This lesson is on volume by cross sections. That's kind of like a slice. Before we get into the calculus of it, I want to remind you of some of your volume formulas, not necessarily, not volume formulas, area formulas from geometry, because we'll be using those. A square is base times height, but since they're the same, you can just say that as side squared. A semicircle, which is half of a circle, is just 1/2 of a circle formula, so 1/2 pi r squared. Now, you may not have been exposed to this one. This is the equilateral triangle formula, and it is side squared on the square root of 3 over 4, or you can write it as the square root of 3 over 4 times the side squared. And that, again, is maybe not one that you're familiar with, but you might want to memorize. So I'm going to put a star beside that. And then some other ones that we're going to do are isosceles triangles, which, your two sides are the same. But we're going to do ones where the base is equal to the height. And if the base is equal to the height, instead of saying 1/2 base times height, you can just say 1/2 base squared. These are not all of the situations, but they're good ones to practice with. I have seen rectangle situations or other triangle situations described in the problem. Just pay attention to what they're describing and use the correct area formula for that shape. Okay, the basic idea here is that we are going to slice an object that's 3D, and the slices would be like thin and wouldn't have any thickness, but we would calculate those areas, and then we would add those up, and the adding up is where the integral comes in. Okay, it's an accumulating area, and once we stack those up, we get volume. Okay, what you may need to visualize here is maybe a stack of Post-it notes or a stack of CDs. If you just look at one, you're looking at maybe the area of a circle or the area of a square, but if you stack them all up, you're looking at a cylinder or a cube, which is a measure of volume. So we're adding up a bunch of slices. Okay, so let's move to a real example. We are going to find the volume of a 3D shape that is bounded by y equals cosine x, the x-axis, and the y-axis. And then we're going to do cross sections. We're actually going to do all those shapes. I'm going to start with squares. So the first thing we want to do is graph this. Okay, and so we've learned about the graph of cosine in previous math classes. We know that it starts at 1 on the y-axis, and it's going to cross the x-axis at pi over 2. And that's all I need of this because they tell me that we're bounded by the x-axis and the y-axis. And so those are the limits of this graph. Now, it says the cross sections are squares. This is the bottom of the shape. If you have to imagine it, you can think of a paperweight because it doesn't have like a nice realistic shape of something we would normally talk about. But I can think of a slice being right here, and so that is one slice. Now, when you slice it, you should have a square as described. That square, the bottom of it is this line I have drawn right here. Now, how this works is, where are we adding up these slices? Well, I'm slicing all through here, so I'm adding them up from 0 to pi over 2. So I'm going to make the integral from 0 to pi over 2. Since it's a square, I'm doing the area formula for a square, which is side squared. Our side that we know is that bottom side, and all the sides on a square are the same. That bottom side is the distance from the x-axis to the graph of cosine x. And now granted, that changes wherever you draw it, but the fact that this is a variable, cosine x, means it's going to change. It's going to change with us as we go. So we just put cosine x in there. So it's basically just your function, and you have to remember to put it in the area formula for a square. Now you can use your calculator to do math number 9 and calculate that area, which becomes a volume because we're summing up our areas, and get 0.785. We didn't have units here, but whatever the units would be, they would be cubed units because we did find a volume. Okay, now we're going to view this same problem, but we're going to use semicircles. And so when I look at the graph and I look at that particular slice again, a semicircle is half of a circle. And I'm absolutely terrible at drawing that. Okay, here we're a little bit better. The bottom of that semicircle, this part right here that would be the diameter of the semicircle, is the same as that line I just drew. So this is sticking up off of the page, the shapes are semicircles, and we're stacking them from 0 to pi over 2. So again, don't overthink it. Your integral is from 0 to pi over 2, and you just use the area formula for a semicircle. And so we have 1/2 pi r squared. Now, the one thing with this is that our formula is asking for r, but have we got the r? No, we have the diameter. We have twice the r. And so this distance here is our function, as it was in the last problem. But if I want the radius is going to be half of that. And so you have to make sure to use half of that function when you are doing the circle and needing the radius, or the semicircle, excuse me, and needing the radius. Now this you can type into your calculator, and if you wanted to, you could pull that 1/2 pi out front and then type your integral in, or just type it in as it looks. Either way, you should get 0.308. And again, I didn't talk about units, so this is still units cubed because what we're finding today is volume. Okay, now we're going to look at equilateral triangles. And again, if I look at that slice, it is the bottom, or the side, of my equilateral triangle. And so that is the same as our function. And so this is our side. I don't have to do anything special because my area formula for an equilateral triangle just calls for side squared times square root of 3 over 4. So now I'm going to go do my integral from 0 to pi over 2, because again, adding up our slices that way. And I use the area formula for an equilateral triangle, so square root 3 over 4 times side squared. And I just have to put that side in, which is our function. Put that in your calculator to get the answer, and you should be getting 0.340 units cubed. Okay, now for the last type of slice that we're going to discuss today with this function. It's the one where we have an isosceles triangle where the base equals the height. And so the slice we're going to have as the base here of our isosceles triangle. And so again, that base is represented by that function. So I'm going to do the integral from 0 to pi over 2, and I'm going to use the area formula that we discussed for the isosceles triangle where base and height are equal, which would be 1/2 base squared. And since our base is cosine x, we just plug that in, and I'm going to stick that into my calculator and get 0.392 units cubed. Okay, for our next example, I'm going to help you get the function drawn, and then I want you to pause and do the volume for when the cross-section is squares, when it's semicircles, when it is the equilateral triangle, and when it is the isosceles triangle where base equals height. So I want you to do all 4 of those, but I am going to help you draw this picture. First of all, this is a line, and it has a slope of -1 and a y-intercept of 1. So if our y-intercept is at 1, I'm at this point right here. And slope of 1 means down 1 over 1. And so we have a line, y equals -x plus 1, that is our graph. And we're again going to give it that restriction that it has to be in, well, it says it's from 0 to 1. So that would be this first quadrant, similar to the last problem. Okay, so now pause and set up your equations. Okay, for the squares, the bottom of the square would be the negative x plus 1 function, and that's one of our sides. So our integral from 0 to 1 will be side squared with that negative x plus 1 as our side. So that's how we set it up for squares. Semicircles is the one with a little bit of a challenge because, again, when I look at my slice, the bottom of that slice is our function, negative x plus 1, but our area formula has just the radius, which is half of that. So if I look at the radius as half of negative x plus 1, I'm going to distribute just to make it a little easier to plug in. So if I distribute the negative 1/2, the 1/2, I get negative 1/2 x plus 1/2. So I would be doing the area from 0 to 1. Area formula 1/2 pi r squared, and that we just figured out is our r. And if I plug that in to my calculator, I get 0.1308, and I just realized that we need to go back and see what we get for the squares. Okay, if you plugged in for the squares, you should get 0.3 continuing, which is the same as 1/3. And I know you're probably just listening to what I'm saying, but if you will pause and type those in, make sure you're typing them in correctly. That's why I'm giving you these answers, because you want to know how to type things in so that you get a correct answer out. Okay, so for the equilateral triangles, you're looking at, again, that slice being having the bottom of the equilateral triangle, and that's the same as the function. So we just stick that in for the side, and it's square root of 3 over 4 times the side squared, integral from 0 to 1. When you type that in, it should be 0.144. Okay, then our last one is looking at that same problem as slices where they're isosceles triangles and the base and the height of the triangle are the same. That bottom of the slice is the bottom of the isosceles triangle, or the base. Your area formula is 1/2 base squared, so you just have 1/2 times that function squared. You're doing the integral from 0 to 1, which gives you 0.1 with the 6 continuing, which can be also written as 1/6. And again, we're in cubic units because we are finding a volume at that point. Okay, for our next example, we're going to change our function to y equals 4 minus x squared, and we're going to look at the interval between 0 and 2. You know this is a parabola that's turned upside down and moved up 4, so it's negative facing, moved up 4, so it's going to cross the y-axis at 4, and the x-axis at 2. So it's similar shape to what we used in the cosine, but it's not exactly the same because it's different numbers, and we're just sketching, so that's why it looks so much the same. Okay, so if I'm doing this without having to draw my little other shape, the first thing I'm thinking about is the integral from what to what? Well, it's on our x-axis, so 0 to 2. And equilateral triangles, the formula is square root 3 over 4 times your side squared. And your side every time has been your function, which is 4 minus x squared. So you can jump to that. I've been drawing the picture so that you kind of could visualize what's going on, and some of you still may not be able to, and you can just jump to this and go with it. We're just going to set these up because we've practiced enough putting them in our calculator. So setting it up is the most important thing, and then being able to type it into your calculator correctly is also important, obviously, if you're in a multiple choice situation or a free response situation. So that's our equilateral triangle setup. Okay, so let's set up the isosceles triangle situation where the base and the height are equal. And again, you look at your x-axis, we're going from 0 to 2, plus it was given in the original instructions. The formula for the isosceles triangle where base equals height is 1/2 base squared. The base is your function, which is 4 minus x squared. So if you can get that part, you should be good from there. Okay, for our fourth example, we're going to do something a little bit different. I have a graph of a parabola that's been moved right 4, as you can tell by the shift here. So it would cross the x-axis at 4, not really cross, but touch the x-axis at 4. And a graph of the line y equals x plus 3. So it would have a y-intercept of 3 and a slope of 1. And obviously these aren't perfectly drawn or to scale, but this is the general idea of what's going on. And we're going to use this interior space between the two of them as the bottom of our figure. So this time we're not being trapped with the x or y axis, it's what's in here. And so each of our slices we're going to be thinking about this being the bottom of them. And so I'm going to come over here and say the bottom of the figures is the top function minus the bottom function, because that's what represents that distance there. And so the top function in this case is the x plus 3. The bottom function is the x minus 4 squared. So the bottom of the figures are all x plus 3 minus x minus 4 squared. Now you can work with it just like that, or you can choose to write this twice and FOIL and then distribute your negative through. And if you do that, you will end up with the polynomial negative x squared plus 9x minus 13. And that's probably the one I'm going to use, because if I were having to do the antiderivative by hand or something like that, this would be an easier situation for me, because it would just be power rules. So the bottom of our figures, again, is this or this, but that's the same thing. It's just been simplified. And we will talk about that radius when we get to the semicircles. But we're going to start with squares. And you'll notice we don't know what A and B are. In every other problem we have known. So let's come back up to our figure, and we need to use our calculators, put 1 in y1 and 1 in y2, and calculate these two intersections. So we're intersecting at this point and this point. So if you do second calculate the intersection and you get the first one, that is at 1.807, and then the second one is at 7.193. So now I know where I'm adding up these slices. So for squares, I'm going to go from 1.807 to 7.193 of my side squared. And as we just discussed, you can use this or this as that side. I'm going to use that bottom one. And there's our setup. And so this one would be one where you would have to use your calculator, math number 9, to do it, because the limits are already decimals. And so they're probably, in a case like this, going to expect you to be using your calculator to solve this. I'm going to just work on the setups here, though. I'm expecting that all of you can type that in. Now, if we look at the setup for semicircles, when we do the semicircle, again, the bottom of it is the diameter, and in our formula we need the radius. And so we know that the bottom is negative x squared plus 9x minus 13. So the radius is going to be half of that, and I'm just going to half each piece. So negative 1/2 x squared plus 9/2 x minus 13/2. And that'll be our radius. So our integral from 1.807 to 7.193, and the semicircle is half of a circle, so 1/2 pi r squared dx, and our r is the half of what we normally use as the bottom. So negative 1/2 x squared plus 9/2 x minus 13/2. And again, this is definitely something that you would use math number 9 on your calculator, plug it in by hand, but you got to be real careful because there's lots of fractions and things going on in here, and you want to make sure to have it exactly the way you see it. And the last one I'm going to do is the equilateral triangles with this. So we're going from 1.807 to 7.193. Area for the equilateral triangle is square root 3 over 4 times that side squared, and we determined that that was x squared plus 9x minus 13. So again, type that in your calculator to get the exact area. Okay, I wanted to come back to the drawing one more time to show you the difference between example 4 and all the other examples that we did. And that difference is that that area was between two functions, not between a function and an axis. So when you determined the bottom of your figures, you do, just like when you're figuring out that area, you do the top minus the bottom function. And sometimes it is in your best interest to simplify, although you do not have to as long as you can type everything in correctly. And that concludes this lesson.